So I'm going to talk about GRDs. Actually, not a whole lot of overlap with what Alessandra mentioned, so that's pretty good. I'm going to basically tell you what are GRDs. So, I mean, we've heard a lot of interesting talks today about different things, but not a lot about GRDs. And so GRDs are transient relativistic explosions. I like to think of these as one of the more interesting astrophysical objects to study, mainly because it takes the entire electromagnetic spectrum to study these things, from gamma rays to radio. So we're basically using different lingo across the different groups when we study these things, from frequency to wavelength to energy. In addition, we might be able to catch gravitational waves, cosmic rays, and neutrinos associated with gamma ray bursts. These things are a veritable zoo of observed properties. So these have time scales. The prompt gamma ray may last from a few milliseconds to several seconds or minutes, and the radioactive glow can last for years. And so these are very dynamic processes happening in these explosions. And so this allows us to study extreme physics and probe fundamental physics using these explosions. So basically, the little toy diagram here, you have the central engine, which is typically a black hole from a core collapse or a merger scenario, and you have accretion onto this, drives relativistic jets out. And through the sort of internal shock scenario where you have these relativistic shocks produce the gamma rays that you see from this relativistic jet. When it plows into the interstellar medium, you have this X-ray optical and radio afterglow that we see at late times. And so here's a sort of nicer picture of this. But this actually, these pictures right here kind of give you an idea of what the prompt emission looks like. And you can see how different these things are. I mean, there's several hundreds of seconds long. This one's really smooth. These are bumpy and spiky and many different pulses. This is only like a second long. So there's a lot of different observed properties, and spent many years trying to figure out exactly what these things are. So observationally, there's two observed classes, and Alessandra mentioned this. There's the short GRD class, so this is duration. So you can see this nice bimodal distribution here where you have short GRDs and you have long GRDs here. And typically the difference between the two is quoted as 2 seconds. So anything shorter than 2 seconds is a short GRD. The careful eye would note that the actual crossing of these two distributions is not at 2 seconds. It's typically at several seconds. But you'll notice that there's significant overlap in these distributions. And so there's not exactly a one-to-one, if we observe a short GRD, is that a merger, is it a collapsar? So this is still a question of tying observational properties to actual progenitors. Similarly, if you look at the duration versus the spectral hardness, so this is just basically the flux at high energies versus the flux at low energies, you'll see that this population here is short GRDs, so they're typically spectrally harder than the long GRDs here. And so basically in the parlance that we use, all short GRDs are mergers, even though that's probably not the case, and all long GRDs are collapsars. But this is something that would be nice to work on, actually studying progenitors. So what do you actually need to detect and trigger on GRDs? And so this is just in terms of STROBE-X. So what you want for the light field monitor is a stable or predictable background, and you want good triggering algorithms. So the light field monitor is going to be viewing in typically lower energies than the sort of sweet spot for GRD emission, which is kind of 50 to 300 kV range. And one of the things about GRD spectroscopy is that in most GRDs you observe this hard to soft spectral evolution. And so the first part of the GRD is hard, and then it evolves to a softer spectrum, which means that if you're viewing it with the light field monitor, what you're viewing is possibly delayed from the actual start time by a little bit, and the soft emission is often less impulsive than the harder emission. So these are not going to be, really bright impulsive flashes. A lot of times these may be, a bit less impulsive. And so you want to think pretty carefully about what sort of triggering algorithms you want to need, especially based on what type of background you have. Another thing that you want to do is you want to optimize the wide field monitor for all sky coverage. Obviously, this is going to see probably roughly a third of the sky. And you don't want to point anywhere near the Earth or the Sun, so you want to minimize your background here. There's some discussion about wanting to trigger on board and the ability to repoint the spacecraft. So if you want to use the XRCA to maybe have some prompt X-ray afterglow, then this is probably a desirable thing that you want to do. And you might actually want to have the WFM modules co-pointed with the XRCA. In other words, you want to basically have the 1/3 of the sky around the XRCA covered by the wide field monitor. And that just sort of minimizes the amount of repointing that you need to do. The other things that you need is low dead time. So you're going to have, with the wide field monitor, you're going to have a background, obviously, and then you're going to be detecting, hopefully, very bright events and sometimes very short events. So you want to have a pretty low dead time. And then if you want to send alerts to the ground, then you need to have some sort of TDRS wake-up capability to transmit alerts, real-time data. So the next slide, Alessandra actually talked about a little bit. I have a slightly different way of showing this. But one of the science cases for STROBE-X is X-ray flashes. And there's some discussion about what these might be. They definitely look like GRBs, but very much softer than your typical GRB. And I'll show you, here's sort of the spectrum that we see from an X-ray flash. And so for the typical GRB, they're sort of smoothly broken power laws. And this peak in UFU is what we call the peak energy or peak. And you'll notice that the X-ray flash, which is this line and this line right here, there's two of them shown, peak at much lower energies than even the X-ray rich GRBs that are seen in SWIFT, and typically GRBs that are seen in FATSI or Fermi or some of the higher energy instruments, they peak kind of in this sweet spot range that's colored in red. And so the wide field monitor would be observing in this blue region. And similarly, if you look at the distribution of these peak energies, you'll see that the wide field monitor is definitely just capturing the low end of this distribution. And you can see the X-ray flash tail right here that you're going to be probing. And so it's very interesting question about what these X-ray flashes are. Alessandra mentioned that they might be off-axis jets, or you have some sort of interesting jet structure. It's potentially that you have a jet inside of a jet scenario where the outer jet is sort of, lower, a lower velocity than the interior jet. So this is a potential science case for STROBE-X.
Yeah. Even the high peak ones have X-ray emissions, so that just because of the high peak doesn't mean totally miss it.
Oh, that's true, right. So you're gonna capture this power law here, and I'll mention this later, but you're not going to be able to constrain the break, and so you're not going to be able to get a good idea of the energetics for a lot of these GRPs, which is a deficiency. So another potential science case is proposed Cocoon emission from off-axis jets. So in this model right here, you basically have this jet. It's just your simple annular toy model jet. So if you're in the jet and you see the gamma ray burst, if you're out of the jet, you probably don't see anything. But there's a potential that you have this cocoon, what's called a cocoon. So this is basically material it's basically accretion material that is being pulled along and shocked. And you get sort of this thermal or quasi-thermal emission that's produced. And so if you're looking outside of the jet, which is still sort of inside this cocoon region, then you can see this. And you can see this basically in X-rays, hard X-rays. So the predictions for this is basically about 1 to 100 keV thermal, quasi-thermal emission. And you have a greater chance of seeing this, assuming that it's bright enough, than you would be of actually being in the jet itself. And so I've highlighted the video Lazade pretty recently put up a paper on archive using simulations. He's done this work for several years actually. He's put up a paper kind of showing what the peak photon energy is of this cocoon based on their off-axis angle. And so the highlighted region here is basically for the light field monitor. So you're basically seeing from about 10 to 35 degrees off-axis from the jet. So this allows us to probe. This is just theoretical. There's not been any positive detections of this, but this is a way of seeing if we can detect any of these things if they exist. Another interesting science case is choked jets. So a lot of this is talked about in terms of multi-messenger neutrinos, astrophysical neutrinos. So if you look at this diagram right here, this is your typical GRB case where you have sort of this extended wind outer envelope material here, and you have this relativist jet that breaks through and produces gamma rays and maybe neutrinos, although we've never seen anything associated with this. You have this potential case over here on the left where this material out here is dense enough and that your jet that you're launching is not strong enough to actually punch through it, so it dies. But the neutrinos actually break through, and we could potentially see orphan neutrinos with no EM emission from this. Probably the most interesting case here is the middle case, where you have the jet that is significantly slowed by the material, so you don't have an extremely high Lorentz factor. It's sort of transrelativistic when it comes out. So you should see hopefully neutrinos, but you'll see softer and weaker emission coming from this, and it should be detectable in the light field monitor band. So this is also potential, obviously, in multi-messenger astrophysics that's accessible. Oops. So one of the other things that GRBs are used for, instead of just studying the physics of GRBs, since they exist at such a large range of redshift, now to the highest redshifts, but among the highest redshifts objects that we've ever detected, is using them to study cosmology. And they can be used in a couple of different ways. So this right here is a Hubble diagram, so you have the redshift, you have redshift along the x-axis here, and then either magnitude or luminosity distance here along the y-axis. And so here in the red, you have type 1a supernovae that typically when you use GRBs for this, you calibrate against type 1a's. And so at low redshifts, what you can do is if you have gravitational wave observations simultaneous with, say, a short GRB, then you can use the distance information from the gravitational wave observation and the redshift information from the GRB follow-up, and you can actually put constraints on Hubble lines here. For high redshift GRBs, what's typically done is there are a number of energetics correlations that are used. So if you have a GRB that's, you have a high redshift GRB, you can place up here, but you don't know the actual distance. What you can do is you can basically use this correlation here to estimate what the luminosity distance is up here. And so, order of 10 is not going to get you anything, but if you have order of 100 of these things, it starts to become constraining. It allows you to probe the dark energy equation of state. So this is an interesting science case for GRBs. Unfortunately, the high redshift ones are probably, at least in context of cosmology, is not accessible to the light field monitor because we need really good estimates of the energetics over basically the volumetric Tammer band. But the low redshift cosmology is certainly accessible. Now, one other thing, I'm not exactly an afterglow person, I'm more of a prompt person, but I want to point out that the XRCA can do prompt X-ray afterglows. Now, I've done some work trying to estimate what's called jet break times, basically just from the prompt emission and energetics correlation from the prompt emission. And these jet breaks, so this is a typical afterglow, so this is the X-ray emission right here. And you can see the strong decay from the X-ray. And you also have a lot of optical measurements here, which this is a really good case. Okay, you don't have all these observations all the time. So this is a really, really gold-plated piece here. But you have an X-ray upper limit down here, and what you'll see is an achromatic break. And this break is called a jet break, and it signifies, you can basically infer how much the jet is collimated based off this jet break. And so one of the key things is that the observed jet break time distribution is this histogram right here, and we're almost certainly biased in this observed histogram. Why? Because we're essentially not catching any really late-breaking jet breaks. And that's because the X-ray flux has really dipped below the sensitivity of a lot of the X-ray instruments and optical instruments. Now, STROBE-X, the XRCA, is probably not going to help in this region. Best case scenario is you could catch something and you could help constrain a jet break maybe out to order of 10 days, so sort of in this tail here. But I think in X-ray afterglow you could definitely contribute, especially in the prompt. And so if you could catch a prompt, a really quick break as well, that would be pretty cool. And I think, you definitely don't want to undersell the X-ray science, or the afterglow, X-ray afterglow science that you can do with GRDs. So, I don't know why this is.
Look at the flux. Oh, it's body.
All right. So basically, just in summary, for long GRDs in particular, so the collapsars, is you have the science cases for STROBE-X is basically the choke jets. There's some multi-messenger astrophysics to be done here as well, especially if you can detect astrophysical neutrinos coincident with these things. There's potential soft cocoon emission and X-ray flashes, potential emission that's off-axis from GRDs. Similarly, from short GRDs and mergers, also this cocoon emission is potentially exists there as well. If you have coincident gravitational wave observations, there's a lot of different things you can do because the gravitational wave information gives you a lot. It helps constrain a lot of things you can do. Cosmology with it, you can help constrain the jet collimation, so the gravitational waves give you information on the actual inclination of the merger system. So you can basically infer how wide the jet is that you're observing. And you can also use the gravitational wave information, which are GRDs, to sort of infer population studies between binary neutron stars and neutron star black hole merger systems. The problem is that there are some deficiencies for when we're talking STROBE-X and GRDs. So one of the big things is that the wide field monitor is not observing in sort of a sweet spot for most GRDs, for most detected GRDs, the 50 to 300 keV band. And because you're not doing that, you're probably not going to catch the peak. You're not going to be able to catch the peak of the spectrum and constrain the curvature, and therefore you're not going to be able to get a good understanding of what the energetics of the GRD is. If you can't contribute to the energetics, then you can't contribute to the energetics correlations, and similarly, you can't contribute to the high redshift GRD cosmology work either. And so, when people are trying to understand rates and luminosity functions of these events, you're going to be able to contribute to the luminosity function at the very low end of the spectrum with X-ray flashes, potentially, but for a large number of detected GRDs, you're not going to be able to contribute to that. One other thing that it's not necessarily a deficiency, but it's something to take into consideration is the triggering efficiency. As I mentioned before, these things are, GRDs at lower energies are typically less impulsive, and so you want to have a good study of how your triggering efficiency works relative to what your background looks like. Similarly, if you're not observing over kind of the sweet spot of the GRB observing band, then it's going to be sort of hard to place these GRBs into classes. You know, are they the short mergers, or are they the long collapsars? And so it becomes even more muddy when you go down to lower energies of these associations. So these are sort of things that are very challenging for STROBE-X to do. I just want to mention that you know, you can actually start achieving some of these things if you allowed the energy range up to 150 keV to be accessible, similar to what Swift has, or even 300 keV would be even better. But I, you know, certainly understand the difficulties in achieving that. So hopefully I've shown you that there's some good science to be done with STROBE-X, with GRBs, and thank you very much.